ChargeTech Portable AC Outlet Battery Pack 27,000 mAh up to 85W/110V. It's approved for airline travel. External power bank charger for MacBooks, laptops, cameras, camping, CPAP machines. Black. Award-winning innovation. Nearly 450C000 raised on Indiegogo. Winner of Amazon's The Maker Challenge. The world's smallest and most powerful AC portable charger battery pack, to include NAC wall outlet. At only 1.56 lbs, this charging station can easily fit in your bag, purse or luggage. Powerful AC power bank. The Omnicharge built-in AC outlet will power any standard electric device. A maximum draw of 85W is recommended. Please check if your device or devices being charged fit within these requirements to ensure compatibility with a portable power outlet. Intelligent fast charging. USB ports are equipped with ChargeTech fast charge technology to deliver 2.4 full amps to your devices for rapid charging. The portable battery charger can act as a laptop power bank. Safety certified. The power bank with AC outlet contains the highest quality available Panasonic and Sanyo lithium-ion battery cells for blue LED lights indicate charge level. Included high-speed cable will charge the unit itself within 2 hours. Take it on the go. The 7.5x 5.2x 1-inch design fits into your purse or backpack, so you can take the portable AC power outlet charger with you on the go. More. The portable power outlet is the first AC outlet you can take on the go. Power devices such as laptops, Bluetooth speakers, like Amazon Echo, and medical devices. It's the last battery pack you'll ever need. With a 27C000 mAh capacity, the possibilities are endless. As featured on CNET and NBC News, voted the best battery pack on the market. The perfect mix. The portable power outlet is the perfect mix of power and portability. It bridges the gap between big expensive power generators and unreliable pocket-sized USB chargers. You can power your laptop, digital camera, curling iron and countless other devices without sacrificing portability. Updated the 12th of December 2016. I edited my original review to correspond with the changes that ChargeTech made to better identify the capabilities and limitations of this product. That additional clarification greatly reduces consumer risk, as well as the risk for disappointment. So I updated my review based on these new reset expectations. That said, the portable power outlet does indeed do what it says it does, and depending on your particular user scenario requirements, it could very well be an ideal solution for you. Above all else, just remember that portable battery powered AC outlets will always have pretty significant limitations when compared to a household or generator based wall outlet. Make sure you understand what your hardware will require versus what this power supply can actually provide, and for how long. If you can do that much, you'll go a long way towards reducing any potential disappointment you may have when you actually put this battery pack to use. This review will focus on the hardware design and performance of the ChargeTech 27C000 mAh portable AC battery pack W/AC plug outlet and USB ports model AC 27K from a typical consumer perspective. This battery pack seems intriguing as it provides both AC and DC sources for your gadgets. One might immediately think that you could power anything with an AC cord, but even with realistic expectations of performance, you'll find that the scope of use to power AC equipment is fairly narrow and limited to 85W maximum. More on that later. The ChargeTech iteration of this hardware appears to be based on a Samaya technology AC18K PCB with a larger internal battery capacity of 27C200 mAh. The internal Electronikz however are identical to the AC18K. Even the PCB is still silkscreened with Samaya Tech's company name and the original AC18K model number information. See attached pictures of the main board. Brit internal design. The ChargeTech AC27K battery pack consists of two primary internal parts. 1. The battery pack, which is built using 8 Panasonic NCR 18650 Li-ion cells, each rated at 3400 mAh. Each cell fully charges to 4.2 VC and 4 cells are tied in series, creating a total of 16.8 VDC. The other 4 cells are also tied in series, then these 2 battery banks are tied in parallel. The total effective maximum capacity of this battery pack is 3400 mAh x 8 cells 27C200 mAh. These are excellent quality Panasonic cells with a very high capacity for the 18650 form factor. But the battery cells, or banks in this particular design, are not individually managed or monitored. As a result, when one or more batteries in the chain eventually starts to deteriorate due to age, the entire bank will suffer. In designs like this, the battery pack is always only as good as the weakest cell, and this is the case anytime multiple cells are tied in series/parallel configurations with no cell balancing electronics. The best you can do as a hardware designer is to ensure that the battery banks never get into those situations where they get excessively abused outside of their ideal operational constraints, i.e. overcharged, overdischarged, shorted, too hot, too cold, etc. The consumer's responsibility to ensure long battery cycle life and maximize return on investment is to take care of the battery pack and keep it charged and stored properly. No extreme temperature exposure, i.e. too hot and too cold. See, and don't store a completely depleted battery for any long period of time, i.e. one day. If you can do this, then this battery design should be able to wear evenly and work well for 500 plus charge cycles. Unfortunately for this device, the 2 individual 16.8V battery banks, each made up of 4 batteries in series, are tied directly together on the PCB, so no individual battery bank or individual battery cell management is possible. This means that the designers are hoping the batteries wear evenly over the charge/discharge cycles. Since they used high quality Panasonic cells, this probably isn't a significant worry. But it's still a considerable concern in my opinion, especially given the availability of decent and cheap battery charge and cell management electronics. 2. The DC-DC converter and the DC to AC converter PCB. As I mentioned earlier, this PCB is made by Samaya Technology. The DC side, 16.8V, 5V, of the board uses a fairly unremarkable DC-DC buck converter, and I measured an efficiency of around 82%, which is typical for a cheaper DC to DC converter design. I was happy to see cleaner DC voltage at the USB jacks than I expected, but I did still see some high frequency DC switching artifacts sneaking through to the output. The 5.0V USB output circuit is powered by a single 2.4A source, and that current is shared between both USB jacks. It's not 2.4A per jack, it's 2.4A shared between them both. That seemed a bit disappointing given what it would take to actually provide 2.4A to each individual jack. I was actually able to pull 2.6A out of the left jack and 2.8A out of the right jack before the unit shut down on me. Each jack is illuminated by 2 blue LEDs that transmit light through a white plastic bezel surrounding each USB port. One very bad design note about the 2 USB jacks is how they're activated. Newer smarter batteries electronically measure an attached load and provide charging current to an attached device when a load is detected, and the charging process is manually initiated by the user. Once the load stops pulling current, the charger automatically shuts down the port. Unfortunately, the AC27K uses a physical switch embedded in the USB jack itself to turn on the DC5V output. That means that anytime any kind of USB jack is connected to the AC27K, that it will be producing 5.0 VC, even if that cable isn't actually connected to anything. So now you have to remember to physically unplug the USB cable or cables from the AC27K battery once your device is fully charged, or you risk running the portable power outlet battery dry just through the process of DC to DC conversion and powering those 4 pretty blue LEDs. Again, ChargeTech was just being exceptionally lazy here. Physical switches inside the USB jack. I didn't even know these existed, and I can't imagine why this particular design choice was made over a more robust load detection and load switch semiconductor solution. The 120V AC inverter design is very disappointing. The AC27K provides an extremely basic modified sine wave which has some very nasty surprises when it comes to powering modern power supplies like laptop adapters and other solid-state power supplies. The ChargeTech AC18K hardware designers went about as cheap as they could for this design, choosing to only provide a single positive and a single negative alternation for the simulated AC in the wave. As a result, you end up with something that looks far more like a square wave than a sine wave, and modern Mac power supplies, i.e. laptop power adapters, are just not made to work efficiently with this kind of alternating square wave form. I've provided pictures of the actual wave form from the AC27K for reference. Below will cover why this single-step AC in wave design is so inefficient, and provide some real-world examples of why single-step modified sine waves are essentially awful in every way, with the exception of design cost. What's the big deal? Efficiency. Consider what's happening here. You're taking 16.8 VDCC, boosting it to 59V by pulling in a lot of current from the battery, then by using 2 FETs, cycle 1 FET to throw the voltage UPC and cycle the other FET to throw the voltage down 60 times a second, effectively creating 118 volts of fake alternating current, AC. Then that fake AC travels to your laptop adapter, where it immediately gets converted back down to DC voltage to power your laptop. This is a very inefficient process. You're essentially paying a large toll just for the ability to use the AC plug, and the missing parts of the sine wave are murdering your power conversion efficiency. The amount of power lost by using a modified sine wave instead of a real sine wave is obscene, and reduces the useful utility of this pack a massive amount. For example, an 85W AC load on the pack only generates 48.1 W of DC through a 24V DC class 5 laptop adapter, and that equates to an efficiency of only 56% C, which further equates to a power waste of 37.8 W. That's terrible. A few more MOSFETs and design changes to use a real sine wave and this thing would have been so much more performant. Unfortunately, ChargeTech cheaped out in the inverter design, and it really shows in terms of lost efficiency. Here's some interesting math to go along with this. My laptop power supply is a Electronikz 120U240 and is efficiency level 5 relac. From the wall, powering a Electronikz 120U240 power supply 117.7 VAC at 0.0567A 6.67 W idle/no load. Laptop not attached. Fake AC from ChargeTech battery pack powering a Electronikz 120U240 power supply 118.2 VAC at 0.385A. 45.5 W idle/no load. Laptop not attached. Difference using real AC from the wall versus fake AC from the AC27K is 38.837 W. Again, the only difference there was AC from the wall or AC from the AC18K. The voltage from both sources was the same. You lose 39 W of energy due to ChargeTech's cheap modified sine wave AC inverter design when looking at maximum loads the AC27K can provide. Here's the losses. Power in 95 W 118.2 VAC at 0.8037 EMA. 24.17 VDC at 2.20 APOUT. Power out. 53.174 WDC. 41.83 WDIF. Efficiency. 0.5555%. WAST. Power waste. 43.51 WPIN. Power in. 85 WAC 118.2 VAC at 0.7191 EMA. 24.17 VDC at 1.99 APOUT. Power out. 48.098 WDC. 36.90 WDIF. Efficiency. 0.56. 56%. WAST. Power waste. 37.79 WPOUT/PIN WAST. POUT. POUT or WAST PIN POUT or WAST POUT. 1/1. PIN POUT plus WAST or PIN POUT. That is hugly expensive. In terms of efficiency, don't believe me, do the measurements and math yourself using your own ammeter. Power your device with relay CC, take a current measurement, then repeat the test with the AC27K. Obviously your mileage may vary depending on what you've plugged in. For example, a 60W curling iron, which is just raw resistance, isn't going to lose much in terms of efficiency since there's no AC to DC transformation occurring. But a laptop power supply will suffer dramatically when using a modified Synwave build quality and watts in the box. Brit as a hardware design engineer, I have an eye for Electronikz build quality. In my unit, I found 5 large solder balls around the FETSCA dirty PCB, flux residue, C1 misaligned lead, and a set of untrimmed leads on an output capacitor that were only about 1.2mm away from shorting out to each other. The battery pack was pretty clean in terms of build, and there's a thermistor tucked inside the battery pack to trigger a shutdown when the temperature gets too high for safe operation. The battery cells were Panasonic, but there is no battery pack or cell charge leveling technology in the device whatsoever, so as soon as a single cell starts to deteriorate, it'll drag down the entire battery pack with it. Once that day comes in the future when one of the cells deke, the rest of the batteries will wear considerably faster, ultimately reducing the entire portable power outlet to non-user serviceable trash. As with all battery powered electronics, the clock starts ticking the day you buy and charge the battery. From that point forward, the onus is on you to properly maintain and use the battery to maximize its life. If you neglect your battery maintenance responsibilities, you'll just end up trashing your investment far sooner than you might hope. Take good care of this battery pack, and these high quality Panasonic cells should serve your needs for quite a long time. Just not forever. The 2-part plastic case design is decent enough, with a single Phillips head screw hiding under the bottom label and several shits around the outer edge holding it together. Very easy to get inside if needed, but not recommended of course. The miniature slide switch used to enable the AC inverter feature is mechanical and may need periodic lubrication. The included semi-attachmatic super compact DC charging adapter is 1x3x1 in size and provides 40W 20V/2A. Tip positive. DC. It is auto switching, international voltage capable, 110. 240 VAC 47-63HZ1A maximum. I didn't take it apart for inspection, but it says it is AL E225703 and CE certified. It comes with an ASIC super short 6-AC inlet cable, often referred to as a Mickey Mouse connector, often used by Dell. The box also includes an international AC plug adapter, carrying bag, and a mediocre quality owner's pamphlet. Practical applications. Well, this one's going to be tough to answer. What can you really use this for? Since it only provides a maximum of 85 WC and its hugely inefficient modified sine wave inverter design could cost you up to 45 W of lost power, there aren't near as many opportunities to use the AC plug on this as you might hope. Low wattage curing iron, very small heating appliances, low current wall warts. As I said earlier, make sure you know what you need versus what you're going to get out of this battery pack to avoid possible disappointment. I took 2 real-world measurements starting with a completely recharged AC27K, graphs attached. 30W AC portable fan, operated for 4 hours 55 minutes before AC27K battery shut down automatically. 85W laptop power supply, operated for 1 hour 23 minutes before AC27K battery shut down automatically. 95W laptop power supply, operated for 1 hour 5 minutes before AC27K battery shut down automatically. BrittleSock, think about the stress the modified sine wave is putting on your hardware. This square wave is brutal compared to a sine wave, and that does stress the electronics in your power supplies. Most AC motors and heaters won't care so much, but modern power supplies aren't designed to function well with a modified sine wave. Keep that in mind when trying to understand if this is a good solution for you. Brit owner's booklet. There's a fair amount of misleading and or confusing information in the owner's manual. For example, page 5 says the portable power bank is capable of powering most 120V AC products that use 95W or less, but the specifications on page 8 state that the maximum AC power output is only 85W. There's also lots of editing errors scattered throughout the manual, but it is still quite usable and gets the job done. Summary: the hardware design isn't ideal. The battery cell / banks aren't individually managed. The AC inverter is terribly inefficient. The 2 USB jacks share a single 2.4A source, and the use of mechanical switches inside the USB jacks to trigger USB voltage is just plain silly. The battery cells are about as good as you can get, but many improvements could have been made to this design to make it more robust and efficient. It seems they opted to cost over quality, and I consider that fairly disappointing.